Okay, so this one example, which is pretty much what we're seeing in section 9.4 of our textbook, we're going to be dealing with polygons drawn on the coordinate plane, which is your xy axis. So in this example, it's kind of nice because we're going to look at how we calculate area perimeter of this shape, but we're also going to go back and review how to classify, so which is something we did back in Unit 7 or Chapter 6 of our textbook when we were trying to determine, wait, is it a parallelogram, rectangle, rhombus, kite, whatever, right? So we'll kind of do this in two parts. So let's start off with the review. How do we classify the polygon? So first off, let's go ahead and draw in your coordinates and look at the shape. All right, so now that I've graphed my shape, remember, you can definitely use your intuition to kind of help you and be like, okay, well, what could this potentially be? However, let's also think about how do we actually determine, right, the classification of the polygon. So we talked about different types of quadrilaterals back in Unit 6. So we had parallelograms, rectangles, rhombuses, squares, trapezoids, and kites. How do we know which is which? So let me go ahead and write that list down and remind you all. Okay, so this is just a short reminder of just one way for each of these shapes. Remember, there's multiple ways to prove parallelograms, rectangles, rhombuses, but these are just some, I thought, easier ones that you can work with. So remember, parallel sides have the same slope. Right angles, perpendicular sides, so you're looking for opposite reciprocal, so like something like 1/2 and -2. And then rhombus for congruent sides, you can just do your distance formula. So those are just some options, right? So that's what we're checking for to classify the polygon. And remember, use your intuition. If you look at the shape, we can clearly see, all right, we don't have a rectangle, which means it's not going to be a square. So we've already eliminated two of our options. So what we're going to do is just kind of, start from wherever you'd like and say, let me see if it's a parallelogram first. And if not, let me move on to, a kite, because if it's not a parallelogram, it's not a rhombus. So those are just some logical deductions you can make. So I'm going to go ahead and check for two pairs of parallel sides. And remember, you don't have to do this. You can do two pairs of opposite congruent sides. You can look at diagonals bisecting each other with the midpoint. It all depends on what you're more comfortable with. But I'm going to go with the parallel sides. So I'm looking for same slope. Okay. So you can count your slope, you can do your slope formula, whatever you'd like. I'm going to go ahead and count because I have my grid here. So this is up 1, 2, so +2 over 1, 2, 3 to the right. So the slope of HE, sorry, that's really messy. So the slope of HE is 2/3, and the side opposite to HE is GF. So that's up 2 over 1, 2, 3. So the slope of GF equals 2/3. So since the slopes are equal, HE is parallel to GF. I'm just not writing my reasons down here, but you can hopefully hear them and jot them down if you'd like as well. But I can substitute to say the slopes are equal and therefore those sides are parallel. And then I can go ahead and say, all right, let's look at the other pair of sides. Okay, so I'm going to look at HG and then EF. So going left to right, HG, I'm going to go down 1, so that's -1, over to the right, 1, 2, 3, so +3. So the slope of HG is -1/3. And then we can do the same thing from E to F. So I'm going to go down 1, it's -1, over 1, 2, 3, that's +3. So the slope of EF is -1/3. And what do you know by substitution? Again, those slopes are equal, which tells us that those sides are parallel because the slopes are the same. So that means we can deduce that this shape is a parallelogram because both pairs of opposite sides are parallel, right? So for sure it's a parallelogram. So now if you're like, wait, could it also be a rhombus? We can totally check. So you can do your distance formula and calculate the length of the sides. And we can see if we have 4 congruent sides. So what I'm going to do is I'm not going to do the opposite sides because I know it's a parallelogram. I already know the opposite sides are congruent. So remember, if we already have a parallelogram, if one pair of consecutive sides are congruent, then we definitely have a rhombus. So let's go ahead and calculate our distance formula. So remember, distance equals, let me adjust that pen, it's a little thick. There you go. So remember, distance formula is derived from the Pythagorean theorem, right? So it's just rewritten, so we're solving for the hypotenuse. So it's your x2 minus x1 squared plus y2 minus y1 squared, all inside a square root symbol, where x1 and y1 are 1 point and x2, y2 is another point. So I'm just going to go ahead and let's calculate the distance from h to e and hg. So h to e is the square root of, and then just go ahead and substitute your values. So I'm just going to go ahead and finish my work and I'll come back. All right, so I just did my distance formula really quickly there, and we can see that HE is not equal to HG, so therefore it's not a rhombus, so our classification is going to stop right here with the parallelogram. Now I know some people like to think, wait, if I just looked at the slope 2/3 and -1/3, that already shows me they're not going to be the same, and length, and yes, you can think of it that way because the translations aren't the same, but remember, slope is not the same as distance. Slope does not tell you the lengths are different. So if you're trying to justify that HEFG is not a rhombus because the sides are not congruent and you're showing me slope, that work is incorrect. So we want to make sure we're consistent with our explanation. So if you're trying to use slope, we want to break that down into a translation along the vector, and then you would say the translations don't give the same vector, right? So we would want to go up 2/3, down 2/3. So you'd be talking about the vector's components being essentially the same, but the directions are different, if that makes sense. So that just makes it a little bit more difficult to explain. So that's why I always tell everyone, if you're going to talk about lengths, forget slope, just do distance. Okay, so that kind of takes care of the review part of this problem. All right, so now we actually want to find the perimeter and the area. So we have to look at kind of part 2 and part 3. Perimeter, and then we also want to look at area. So I'm going to go ahead and erase all my work and then redraw my figure, and we'll kind of start on a blank slate here. Okay, so how do we do perimeter, area? So perimeter, pretty straightforward, right? Perimeter, we actually have to calculate the side lengths and add up all the sides. So I know I just erased all my work, but remember I already calculated the length of HG, and that was the square root of 10, and I calculated the length of HE, which ended up being the square root of 13. And remember, we determined this is a parallelogram, so this is also why it might be nice to classify first, because then you can use the property of your shapes. But because it's a parallelogram, we know the opposite sides are congruent, so that tells us HG is going to be congruent to EF, which makes it equal to EF. And same, HE would be congruent to GF, which makes it equal to GF. So that means my perimeter is just square root 10 plus square root 10 plus square root 13 plus square root 13. And then we just want to combine our like radicals. So just like you'd combine your like terms, if this was x plus y plus y, that turns into 2x plus 2y. Our perimeter now turns into 2 square root 10 plus 2 square root 13. Remember, perimeter is in plain old units. We don't know if this is inches, feet, centimeters, or whatever, so we'll just put UN for units. So that's perimeter. So perimeter is pretty straightforward. Just distance formula if you need to do it, count if it's horizontal, vertical, and just add them all up. Area is where it can get a little bit more fun. So when we're doing area, you might think, well, wait, I know the formula, Ms. Huang. Area of a parallelogram is base times height, but we look at this and we're like, wait a minute, where's that perpendicular base and height? I don't see it, because you might think, well, EG is right, a vertical line, so that gives me a right angle, but that gives you a right angle with, right, this gives me a right angle with this bottom part here on my grid, but that's not part of HG or GF, right? So that's not actually going to indicate base and height. So when this happens and you're like, oh, I can't use the formula for the shape, that's okay, because remember, this is why we had composite figures that we had just talked about. So what I want to do is I can break this up into familiar shapes. So one way to do this is to take it and say, okay, well, what do I see inside this parallelogram? Well, if I actually just draw in EG, I create two triangles. And then what's important here is you'll realize, okay, if I look at this triangle EFG, EG can be the base, and this distance here could be the height from, I'll call this point, let's call it P. From P to F, that's the height, because I have a perpendicular pair of lengths. So what I'm going to do is I'm going to use the triangle. So my overall area is going to be the area of triangle area of triangle EFG plus the area of triangle HGE. Right? So I've just broken this down into two different triangles. So the triangle, oops, let me redraw that. EFG that I just kind of marked up in the graph has a base of, count it, 1, 2, 3, and a height in count over 1, 2, 3. So area is 1/2 base times height equals 1/2 of 3 times 3. Half of 9 is 9/2, or 4.5. And then if we look at the second triangle, this triangle GHE, same deal, right? GEH. GE is still the base, so that's 3 units. And then if I go from H and go straight across to hit EG, I can call this point Q. HQ becomes the height because you can see that right angle forms. So that height, counted again, 1, 2, 3. Area is 1/2 of 3 times 3, which is again 9/2. So that means the overall area of EFGH is just 9/2 plus 9/2, or 9 square units. Okay? So that is one way to deal with our composite shape. I have one last method to show you. So let me kind of erase this area and we'll take a look at how we can deal with subtraction. All right, so what if you're looking at this and you didn't recognize we had two triangles contained within the parallelogram, or you were like, I see the triangles, but I'm not really sure what the base and the height are. Well, an alternative is you can always draw a rectangle, or try to draw, or I would always say a rectangle because I'll show you why, but try to draw a shape around your figure. So what I'm going to do is I'm going to draw the smallest rectangle possible that'll go around EFGH. So you'll see me just draw this box, and each vertex hits a side of that box. Why am I doing this? Because each of these corners is 90, and it creates 4 right triangles. And because we have those right angles, we know we have a base, we have a height, right? We have a base, we have a height, we have a base, height, a base, and a height for every single one of those right triangles. So what we can do is we can say, okay, the overall area of the rectangle, take away the 4 triangles, leaves behind what's left over, the parallelogram EFGH. So our plan here is to take the area of the rectangle and then subtract the area of your 4 right triangles. And then what we'll be left with, if you imagine taking paper and cutting off those corners, we're left with that parallelogram. So we know the area of a rectangle is just base times height, and we can count it going from H all the way, or going from corner to corner, right? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So that's 6, and the height going down 1, 2, 3. So our area of the rectangle is 18. And then we can look at each triangle, right? So I'll just call this triangle 1, triangle 2, triangle 3, triangle 4, and I'll calculate each area of the triangle. So triangle 1, right, area is 1/2 base times height. The base, I can count that as 2. The height is 3, so half of 6 is 3. The area of triangle 2, area is once again 1/2 base times height. Base is 3, height is 1, so we get 3/2. Triangle 3, and you guys can basically see I'm just doing the same thing over and over again. 1/2 of 3 and 2 is 3. And then with triangle 4, once again, area 1/2 of base times height, 3/2. So the sum of that would be 3 plus 3 plus 1.5 plus 1.5. So 3, 6, 9. And then my total area of EFGH is just 18 minus 9, or once again, 9 square units. So it's up to you what method you want to do. I think it's nice to see both. Sometimes it's easier to take away the corners. Sometimes it's easier to split up the shape into familiar pieces. All right, so that is area perimeter in the coordinate plane, and also a little review of classifying quadrilaterals.